Okay, we're going to talk today about our first topic that's strictly a BC topic. This is a topic called L'Hopital's rule. It's used to compute limits. Now I understand this is a French word, obviously it's a name, and in America anyway, we typically say L'Hopital. I don't speak any French, so I'm sure I'm butchering the name, and you're welcome to pronounce it correctly with a French accent, but I can't do that, and I don't do that. So what you hear in American mathematics classrooms is the pronunciation L'Hopital. Okay? All right, so let's take a look at this. This is a pretty neat rule. Here we go. So here's what it says. Assume that f of x and g of x are differentiable on an open interval containing a, and that when you plug in a, you get 0, okay, in both functions. Okay, we also have to assume, for this to work, that the derivative of g is not equal to 0 pretty much anywhere except it can equal 0 at a. If you want to. So here's what it says. Then if you take the limit as x goes to a of f of x over g of x, then the limit is the same if you take the limit of f prime of x over g prime of x. So again, provided the limit on the right exists. So that means that if I have the limit of a ratio, okay, of two fractions, and if I were to try to plug in a into the top and the bottom, I were to get 0 over 0, then I can actually, to compute that limit, I can take the derivative of the top and the bottom and compute that limit. It's the same. Okay. It also holds for the case when you have infinity over infinity, or negative infinity, or negative infinity, or infinity over negative infinity. Any kind of ratio of infinity over infinity, it also holds. Okay, so let's look at the proof. Okay. Actually, before we do the proof, let's talk about the in practice, frankly. In practice, what that means is that if the limit of this is really 0 over 0, essentially, if you try to plug in a, you get 0 over 0, or you get infinity or infinity, we call those indeterminate forms. Okay? If you end up with an indeterminate form when you try to take a limit, then what you can do is you can take the derivative of the numerator and the derivative of the denominator and take the limit of that. Okay? It's a way of simplifying things. So that you can take the limit of a rational function, or of any function that forms a ratio. Right, so that's what L'Hopital's rule says. So let's look at the proof now. Oh, that's not what I want. Okay, here's the proof. All right, now, what we have to observe first of all is if this is going to work, so if the limit on the right exists, right, that limit, if this thing exists right here, okay, if this exists at all, okay, then if this thing exists right here, what that means is that I can plug in a and get a result. Okay, so it means that if this works, then the limit as x goes to a of f of x over g of x is f prime of a over g prime of a. And that's what we need to prove. Okay, so that's what we're going to try to prove. So let's start at the beginning. One of the suppositions here, presuppositions, is that if we start with this ratio here, and if I plug in a, or if I plug in a, here and here, I get 0 over 0. Okay, it also works for infinity over infinity, but we're just going to use the 0 over 0. Okay, what that means is if I plug in a, I get 0 on the top and 0 on the bottom. So here's something I can do. Okay, since that's true, then f of x over g of x, as we approach a, is the same as f of x over, minus f of a, because f of a is 0, and g of x minus g of a, because g of a is 0. So these are the same because our statement is that if I plug in a, I get 0. If I plug in g of a, I get 0. So these are the same. Okay. And since x does not equal a, x approaches a, okay, I can actually introduce this other term. Okay, so here's my statement here. It's the same that I have right here. I just rewrote right here. Okay. And what I can do is I can divide the numerator by x minus a, and divide the denominator by x minus a, and that's legal because x cannot equal a, because x is approaching a but never equaling a. Okay, so it's just kind of one of those things we introduce it kind of seems silly. Now, if I take the limit of this, okay, f of x over g of x, okay, I know that's the same as the limit of this, which I've written up here, okay, and that's the same as the limit of this big ratio. Right here, okay, that's right here, okay, but notice the limit of the numerator, if I take the limit of a rational function like this, or a rational expression, then I can break it into the limit of the numerator divided by the limit of the denominator, provided they both limits exists. Okay, and that's one of our things that we have to assume for this theorem to actually make any sense. So the limit of the numerator exists and the limit of the denominator exists. But the limit of the numerator, this is the definition of the derivative of f of x. And the limit of the denominator, that's the definition of the limit of g of x. And there it is. Okay, evaluated at a. The limit of the numerator divided by the limit of the denominator. And this should be f prime at a and f prime at g. Okay, so you're not responsible for being able to produce this proof. I just want to show you that it's something we can actually do. It's not something that just somebody made up. Let's do an example in practice. So here's a good example. Now this one can actually be done without L'Hopital's rule, and many of these proofs can be done, or these problems can be done without L'Hopital's rule. But I want to use L'Hopital's rule to show you that this is actually a fairly straightforward computation. Okay, so the limit is x goes to pi over 2 of cosine squared of x divided by sine of x minus 1. So the first thing I do is I plug in pi over 2 and see what would happen if I plug it in, because the numerator is continuous and the denominator is continuous. So if I plug in and I get a number, it'll work. But notice if I plug into the numerator, I get 0. And if I plug into the denominator, I also get 0. This is what we call, again, an indeterminate form. And when you have an indeterminate form, we can use L'Hopital's rule, as long as we are able to take a derivative of the numerator and take a derivative of the denominator. Okay. So what I'm saying is that here's the original statement. This limit is the same as if I take the derivative of the numerator, which here I have to use chain rule, 2 cosine x times the derivative of cosine of x, which is negative sine of x, and divided by the derivative of the denominator. The derivative of sine of x minus 1 is cosine of x, because the 1 goes away. All right. So these two limits are the same. But look, I have 2 cosine. I can cross out the cosine of x, because cosine of x equals 0 only when x is equal to pi over 2, okay, or other places. But near pi over 2, it's not equal to 0, so that's legal. Now I have the limit as x goes to pi over 2 of negative 2 sine of x. I can plug in a pi over 2 here and get negative 2. So here's the nice application of using L'Hopital's rule to compute the limit of a derivative like this. Okay. Now, you might have noticed here that we actually have another way of doing this. Cosine squared of x I can write as 1 minus sine squared of x. And now I can look at this as a difference of squares and factor the numerator into 1 plus sine of x, 1 minus sine of x, and then I just have to multiply by a negative 1 in order to get the numerator and the denominator to have common factors, and I can cancel. So there's another way to do this problem, is my point. But L'Hopital's rule is very, very nice and simple. Okay. Let's look at another problem that may be a little harder to factor any other way. We're going to look at the limit as x goes to 0 from the right of x ln of x. And now we have to, in this case, look at x going to 0 from the right, because ln of x is not defined for numbers less than 0. It's actually not defined for 0 either. Okay. Now, L'Hopital's works for one-sided limits. Okay, we don't have to worry about that too much. All right, so we have this statement here. And if I try to plug in 0, well, first of all, I can't plug in 0 here. Okay. Because I can't plug in ln of 0, but I can see what would happen as I approach 0 from the right here. Okay, well, that one's going to go to 0. And if I try to approach ln of x from the right, okay, I'm going to get negative, this should actually be negative infinity. Okay, and 0 times negative infinity is not an indeterminate form. Okay, now we would like it to be, because we'd like to be able to just take derivatives and be done with it. This is not even in a fraction, so there should be a little bit of a red flag here, right? We can't use L'Hopital's rule directly in this case. However, we can play a little bit of a game here. I can notice that x times ln of x is the same as ln of x divided by 1 over x. Okay, so take a look at that. Make sure you're confident that that's true, right? If I multiply the numerator and the denominator here by x, do I get the same thing? I do. Okay. This is a nice way to rewrite it. Now, if I look at what happens to ln of x as x goes to 0, well, it goes to negative infinity. If I look at what happens here, okay, as x goes to 0 from the right, we go to positive infinity. Okay, and infinity over infinity, or any version of infinity over infinity, is an indeterminate form. Now I have it in an indeterminate form. Okay, so now I'm going to take the derivative, or pardon me, I'm going to take the limit of this. I'm going to take this limit. Okay, so first thing I do is I have an indeterminate form here, and I take the derivative of the numerator and the derivative of the denominator. The derivative of ln of x is 1 over x, and the derivative of 1 over x is the same as negative 1 over x squared. And so remember, we're using the fact that 1 over x is the same as x to the negative 1. Okay, and you can see that's what you're going to get there. Okay, so this is the application right here. This step is the application of L'Hopital's. Okay, and now we do a little simplification. Well, if I want to simplify this, I can multiply the numerator and the denominator by the factor x squared. Oh, this is terrible. I'm sorry about that. X squared versus x squared. All right. What am I left with? Okay, the denominator, the x's cancel, the x squareds cancel. I'm left with x squared over x, which is just x, but I still have a negative. So this is the limit as negative as x goes to 0 from the right of negative x, which is 0. Okay, this is one we couldn't have done by factoring. Okay, but now we have a way of figuring out what the limit of x ln x is as x goes to 0. Again, it's unclear what happens to numbers as one number is going infinitely large and one is going infinitely small. But now we know in this particular instance, it's not always going to be true that in this case, 0 times infinity is in fact 0. Not always going to be the case. Okay, so this is an application of L'Hopital's rule here. Okay, and that's it. So L'Hopital's rule is a fairly straightforward concept where whenever I'm taking a limit of 0 over 0 or infinity over infinity, I can take the derivative of the numerator and the derivative of the denominator and take that limit. The other thing that you can do is you can do it over and over again. So if the first time L'Hopital's rule doesn't get you what you want, okay, if you're still left with 0 over 0 or infinity over infinity, you can do L'Hopital's rule again and take a second derivative at the top and the second derivative at the bottom. And hopefully, eventually, you're going to get those derivatives down to something that gives you something much more determinate. That's it. Okay, thanks everybody.